Achieving zero latency on-device AI requires a radical departure from standard software engineering. We have to bypass standard operating system abstractions entirely. Symmetric multiprocessing kernels, like a standard Linux or Android environment, are designed to juggle thousands of background tasks. When you attempt to run massive tensor computations on these standard scheduling tracks, the OS inherently introduces interrupt jitter and unacceptable latency delays. This schematic details the physical solution, the asymmetric multiprocessing unikernel. We bypass the complex closed-source driver wall by partitioning the silicon into two specialized domains. Cores 0 and 1 act as domain 0, hosting a minimal Linux runtime for physical I/O. During boot, the kernel passes ISO CLPUs equals 2,3, physically severing cores 2 and 3 from the OS scheduler, waking them straight into a freestanding C++ math engine. Directing the math to isolated cores is the only way to secure the absolute deterministic execution required for an edge coding agent. No background tasks or OS timers can ever interrupt the logic. With the CPU cores isolated, we must impose the same strict architecture across the physical memory map. Here we see the physical RAM map governing the system's data flow. We carve out 4 distinct hard-coded hexadecimal blocks: the domain 0 host kernel, shared asynchronous data buffers, a non-evictable KV cache, and a contiguous wait arena. To defend this territory, bare metal Core 2 executes direct assembly primitives, natively masking all software interrupts. This hardware-level lockdown strips away all software unpredictability. It creates a single-task, zero-jitter execution lane. Strict physical memory bounding replaces the noise of a standard mobile chip with the predictable execution of a high-speed mathematical engine. The cycle begins at the ingestion phase. A physical I2S controller captures your vocal waveform at 16 kHz, exactly when you speak a complex code debugging prompt. Instead of using the CPU to move these bytes, the chip's hardware direct memory access, or DMA, engine streams the raw audio directly into the asynchronous data buffers. The CPU cores remain untouched, conserving battery power and maintaining their cache locality. This diagram illustrates the first major microarchitectural hurdle, the ARM64 weakly ordered memory model. Because reads and writes are weakly ordered, a severe cache corruption risk emerges. If Core 0 writes audio tokens to shared RAM and Core 2 attempts to read them immediately, Core 2 ingests stale data from its local caches before the fresh RAM data registers. This microsecond timing mismatch injects corrupted semantics into the pipeline, resulting in total language output corruption from the large language model. Raw compute power serves no purpose if the system's fundamental memory architecture cannot synchronize read and write states perfectly across cores. To prevent this, we enforce an absolute ban on naked pointer polling between the isolated cores. We implement a strict hardware solution. When Core 0 finishes writing to the shared buffer, it executes a data synchronization barrier instruction. This forcefully flushes the dirty cache tracks out to the physical RAM. Immediately following the flush, Core 0 fires an interprocessor interrupt pulse directly across the bus to Core 2. Core 2 intercepts this hardware signal and responds by invalidating its local cache lines. Only then does it execute the read, guaranteeing a pristine ingestion of the token sequence. Perfect cache coherency across split processing cores demands explicit, microsecond-level hardware choreography. Once the fresh tokens are secured, Core 2 enters its linear algebra decoding loop to process the precompiled Gemma 4 matrices. Standard scalar unpacking routines introduce massive latency overhead.
We abandon them completely. Instead, the model utilizes symmetric int4 quantization. By forcing the quantization 0 point to 0, we eliminate the heavy cross-accumulation math that bottlenecks tensor multiplication. This maps the physical data movement. The packed 4-bit weights stream directly from the contiguous weight arena into the 128-bit ARM neon vector registers. The weights expand instantaneously on the fly using inline SIMD bit shift instructions, unpacking only upon hitting the vector execution lanes. Confining the data expansion strictly within the internal CPU registers obliterates the external memory bandwidth bottleneck. We apply the same register-level confinement to the attention mechanisms. Calculations utilize online softmax tiles, preventing the intermediate matrix from ever spilling out to external RAM. But even with data perfectly pinned in physical memory, large language models suffer from a mathematical vulnerability: attention dilution. This quantitative model shows the transformers underlying softmax mathematics. As your generated codebase expands, the attention score of early anchor tokens exponentially decay towards zero. The context simply dilutes. We engineer the fix upstream. During the fine-tuning phase, we implement attention bias matrices directly into the Gemma 4 checkpoint. We hard-code a permanent mathematical bias factor, an unaffectable positive bias value mapped strictly to the initial anchor tokens, directly into the causal self-attention mask layer. Injecting structural mathematical bias into the matrix forces the model's internal vector representations to prioritize your core linker geometry permanently, no matter how wide the context window scales. The third and final architectural challenge is latency degradation. Forcing the system to execute compiler-level syntax checks in line after every single token generation step destroys the physical velocity of the output. We resolve this by decoupling the verification process entirely, creating a two-stage non-blocking buffer that leverages both bare metal cores. On the top lane, Core 2 generates tokens on a continuous linear trajectory, emitting them at maximum physical speed into a shared staging buffer. It never pauses to check its own work. Meanwhile, Core 3 operates asynchronously on the bottom lane. It sweeps up the trailing token fragments just a few frames behind Core 2, incrementally parsing them to assemble an abstract syntax tree. If Core 3 uncovers an incomplete logic block or memory alignment violation, it fires a high-priority hardware interrupt straight to Core 2. This forcefully flushes the execution pipelines, forcing an auto-correction step. Asynchronous core shadowing allows the system to guarantee code safety without sacrificing raw generation latency. Fusing a minimal Linux host for hardware I/O with a perfectly synchronized bare metal compute engine yields absolute local hardware sovereignty. This specific microarchitectural foundation applies directly to complex, high-frequency physical systems, where exact timing is the primary constraint. The atomic mailbox ring buffers, cache coherency protocols, and memory barriers engineered for this architecture are entirely hardware agnostic. This symmetric memory framework scales to any high-frequency physical sensor. The ingestion blocks adapt to capture spinning LiDAR arrays, and the staging buffers translate token outputs into precise instructions for robotic joint actuators. Operating at physical hardware limits, the mailbox protocol provides microsecond precision to capture measurements from a quantum processing unit before environmental coherence decays. Aligning software logic directly with the physical laws of silicon turns raw hardware constraints into a precision engineering tool.